The concept in this lesson is continuity, and its connection to what we've been studying is that limits are the language in which we will explain continuity or justify it. The easiest way to define or to think about continuity is to determine if a function can be drawn without lifting a pencil, or if you're given a function, can you trace it without lifting your pencil off the paper? That means no asymptotes, no missing points, any funny business like that. So it's continuous if you can trace it or draw it without lifting your pencil. As a general rule, the following function families are all continuous everywhere in their respective domains. That includes polynomials, rational functions, absolute value functions, trig functions, and square root functions. And that means wherever they exist, they're continuous. Now, if there are parts of the domain that do not exist, then they, of course, would not be continuous on those intervals. This next statement is a nice summary of what we just talked about. So a function is not continuous, or we can call it discontinuous, for any values of its domain that it does not exist. When I was introducing the learning target for today, I mentioned that limits are used to explain or to test for continuity, but a lot of times students get confused between a limit and a continuous function. So I want to go back to that generic drawing I keep using, a visual of what a limit requires to exist, and that is just that the left and the right pieces of functions meet up at the same y value. And to repeat again, the point may or may not be there, so the point does not have to exist for the limit to exist. And next I want to contrast that to what it looks like for a function to be continuous. So visually you can see right away that the extra requirement for continuity is that the point does have to be closed and be in the precise place that the left and the right limits meet up. So algebraically, it's no longer just the left and the right have to be equal. The left and the right have to be equal, and the point, which is where they meet up, has to be equal to the same value. So it's an extra requirement that we have to test for. So I hope that gives you a nice visual of what it means graphically and also algebraically for a limit to exist and for a function to be continuous. Let's look at the definition of a continuous function using limit notation. And this can be a little bit confusing, but we're saying that the limit of the function f of x as x approaches c is equal to the function value at c. And if you're not as comfortable with that notation, just remind yourself that if the limit exists, that is your left and right limit being equal. And we're saying that it needs to be equal to the function value, and the function value is really just where the closed point is. So it's just a much more formal way to write this thought that the left and the right need to be equal, with the point being equal as well. So left equals right equals point. And the statement right underneath that is just explaining that more using words than mathematical notation. So the limit value must equal the function value to be continuous. Let's see if we can apply these ideas to an example. We're given a piecewise function f of x, and we're asked if f of x is continuous at x equals 1. So I can see in my piecewise that's where the left and the right pieces of the function meet up. And through that process, I'm going to have to conclude why or why not. So let's get our thoughts together. When we first started working with piecewise functions and determining limits, we started by determining which piece of the function was left and right and where the point existed. So we have left is our square root of x, our e function is the right, and that is where the point is as well because of the equal sign. And as soon as you see the word continuous in a question that you're being asked about a function, you want to mentally think, okay, I need my left and my right limit to be equal, but I also need the point to be equal. And this is just a thought process. This is not formal mathematical communication that we're required or expected to be able to present. So we're going to take that thought and use our limit notation to communicate a little more clearly. So I'm starting with basically a template of a 3-section equation, knowing that I want my left limit expressed as x approaches 1, because that's what I was given. That is from the left using that superscript. I left a space to write the actual function on the left. I also left a space to represent the point of the function at 1, and then I expressed my right limit using that superscript as x goes to 1. And of course, I have space over here too to write what function piece is on the right. So using what I determined as I read the question to be the left and right piece, I filled in the functions for the left and right limits, but I still need an expression for my point. So let's go back up here to where we were talking about how to express the point in mathematical notation. And you use the name of the function, which is f, and the c value, which we're being asked about, is 1. So that point is best represented by the notation f of 1. So this three-part equation represents my hypothesis. I am testing to see if the left and right limits equal where the point or the function value is. And to go ahead and proceed with that test, I need to substitute my 1's in for my x's, and then we'll talk about how to evaluate the function as well. I went ahead and evaluated the left and the right limits by substituting the 1. The square root of 1 is 1. I got e to the power of 1 minus 1. E to the 0 is 1. And the function value, you might remember, is attached to the right piece for this function. It's not always attached to the left or right piece, but often it is. And so it might seem a little redundant, but we actually just have to substitute that 1 into the right piece of the function here. So it'll actually be exactly what I have in this right section of the equation. So after I've simplified all three parts, I do find that they are all equal to 1. So my left and right limits are equal to 1. The point has a closed, or the function has a closed point at 1. And so this function would be continuous. And so although we can't see it, we have proved it algebraically. But it's not quite good enough just to come up with the numeric conclusion. I need to state and communicate that I understand what I have just found. This equation that we wrote in the very beginning, the three-part equation with our limit notation, remember that was our hypothesis that we tested. It turned out to be true, and I don't want to have to rewrite that and all that notation in a justification sentence. So I've gotten clever in my last few years of teaching, and I decided to go ahead and just start my conclusion there. So I like to put a big set of brackets to bring attention to it, put my therefore symbol, and since it did turn out to be true that all three were equal, we're going to say that the function is continuous at x equals 1. So that's a simple way to make your justification without having to rewrite a lot of mathematical notation. Just follow it up with the function f of x is continuous at x equals 1. You can probably guess in our next example that it's going to turn out to be not true, but let's save that one for class in case you have any questions about how to set it up or solve it out or justify it. The example after that is a little funky too because it has this value of k in it, so I think that would be best to leave to work out together in class. So let's end the video by talking about what makes a function not continuous or certain things that cause discontinuities. A function can be discontinuous over an interval in the domain, or it could just be not continuous at a specific x value. Let's call that x value c. So if a function is not continuous at x equals c, then it has a point of discontinuity at x equals c. And there are different types of discontinuities, actually 4 different types, 3 that you'll see more often than the 4th type. The 3 most common types of discontinuities are called a point, a jump, and an infinite discontinuity. The one you'll see less often, in fact, I didn't even find a good graphic of what that looks like, so I'll show you in class what an oscillating function looks like, or an oscillating discontinuity, rather. But I'd like you to try to pick out on this graph where you think these types of discontinuities might occur. So point is also called removable, and it's where a point either does not exist or it's been moved. A jump is best described as a break in the graph, and an infinite discontinuity is where an asymptote occurs. So take a look at that. We'll check your answers when you get to class. And I want to talk about one more thing. So the last thing we're going to discuss is something called the continuous functions theorem. And it's not a theorem that we have to work out examples for necessarily, but it's a fact that is nice to know about continuous functions. And that is, if you have 2 or more continuous functions and you combine them in different ways, for example, multiplying them by a constant, adding, subtracting them, multiplying or dividing them, the result is always continuous. So continuous functions have that unique property that any combination is continuous as well.